why it's sort of a nice little PowerPoint presentation, but there's a little bit more in it than is really necessary for this group. So I'm going to kind of bleep through some of the slides pretty quickly, though if you see anything that you think is interesting, we can always go back. So the question is going to be, do rocks come to the Earth from other star systems? That's the big picture question we want to ask. And I've got a question mark there. You have to wait for the answer for a couple of slides here anyway. So for this group, you've seen this all before, but just some terminology in case you're unfamiliar with this. A meteor is technically only the phenomenon which occurs while this solid particle from wherever, our solar system or elsewhere, which is burning up in the atmosphere, and the phenomena associated with that. Before it hits the atmosphere, we call it a meteoroid. If anything survives to the ground, we would call it a meteorite. So I'm going to tend to mix these terms up a little bit. Okay, you've all seen this before, but this is why meteoroids are the most important objects in the universe, because they're the biggest thing on this graph. Except for black holes, of course. I don't know why they put that on there. They should trim that. But anyway, meteoroids span a wide range of sizes, from the very, very small to the very, very large. And that's going to impact our discussion of whether they can come from other stars as well, because the size is going to be important. This is the Peekskill Fireball, which you can't see.
No, it was up there, yeah.
So this is just, I mean, this would be the most exciting thing, of course, if something like this actually came to us from another star system. This is some amateur video taken of the Peekskill Fireball. The Peekskill Fireball is famous for dropping meteorites, and is, I believe, the first meteorite ever to strike a car. So there's the famous Peekskill car. Peekskill did not actually come from another star system, as far as you're aware. And a recent fireball event, which is well known to this group, and which I mentioned at Master for obvious reasons, is the Grimsby Fireball, which was seen by many of the cameras run by the UWO group and passed almost directly over Hamilton before meteorites were actually dropped in the Grimsby area. And you've heard talks about that. It was quite an interesting project there. But for completeness, I'll show the Grimsby Fireball as seen from the McMaster camera. So the fireball passed almost directly overhead, and that's why you can see it passing right through the middle of this fisheye lens. So the horizon is around the edges, and straight up is directly towards the middle of this image here. So where do most meteoroids come from? The bulk of meteors that we see in our atmosphere do not come from other star systems. They come from inside our planetary system. And at small sizes, the sources are comets. At large sizes, they're asteroids. And an asteroid is what you think it is from the movies. It's a few kilometers across. It's a big rock. A comet, typically what you think of a comet is something which looks like this. But at the heart of the comet in here is a small, essentially an ice asteroid. Not that different from a rocky asteroid, perhaps, except in that its composition is more ice than rock. And as a result, if a comet nucleus gets close to the sun, that ice will vaporize and release the material in it, which includes various things which turn to gas and which fluoresce. It produces this beautiful blue gas tail. Comets typically have two tails, a blue gas tail, and then this white tail here is essentially dust, dirt, meteoroids, if you will, that is reflecting sunlight, and that's why it appears white. That's basically just reflecting sunlight. So this is just a cartoon of how meteoroids are released from the comet nucleus. But they're released in a fairly gentle fashion, and so they don't actually go that far from their parent comet's orbit. So here we have just another simulation. So here's a comet on a fairly typical orbit, and it's going to pass near the sun, and you'll be able to see the tail and so forth. This is just a schematic representation of it, but it does show a couple of things. One is why you can only see comets for a relatively brief period of time. Halley's Comet, for example, comes around every 76 years, but you can only see it for a few months around that. And that's because comets move very slowly at the ends of their highly elliptical orbits and very quickly when they're near the sun and visible. But also, as they travel around this path, the material that they deposit spreads out to first order along the comet orbit. So you end up with a trail of debris and dirt, meteoroids essentially, which continue to orbit the sun, but fill out this sort of torus shape around the sun, which we call the meteor stream. So if the comet's orbit happens to take it through the Earth's orbit, of course the comet might at some point hit the Earth, though the odds of that are still quite low. But because there are so many meteoroids spread throughout the orbit, it's inevitable that Earth will hit some of these smaller particles. And if you were to take a time-lapse picture of the sky during one of these meteor showers, you would see the meteors coming from what appears to be sort of a fixed point on the sky. And that's because you're essentially looking down the fire hose, if you will. And so they're coming all essentially parallel to each other, but you're sort of standing under the shower head, and so raindrops are going all directions. A good meteor shower, one that would sort of get in the news, if you will, might be expected to produce about 100 meteors or so per hour, which is not that much. I mean, it's 1 or 2 per minute. It's not dramatic, but it still makes for a nice show. The Perseids are the best-known meteor shower in August because the weather's nice. I will point out, and you'll hear more about this in the future, no doubt, is that there's an outburst expected for the Draconids, and it might reach as many as 1,000 per hour, according to some predictions. So look for more information on that in the future. So comets only release relatively small particles. They don't release rocky particles which are bigger than maybe a few tens of centimeters across. If you want to get a meteorite on the ground, you need something which hits the top of the atmosphere with a size that's maybe a meter or more across. And even then, you're only going to get a small fraction of that mass to the ground. So the Grimsby Fireball, for example, which did drop a few meteorites, sort of of order a kilogram and has been found, must have been much larger than that, sort of a ton of material at the top of the atmosphere. And these larger particles come from the asteroid belt, and they're produced by asteroid collision, essentially. So whatever its size, when a meteoroid hits the top of the atmosphere, it begins to ablate. So ablate is the technical word for the vaporization at the surface and so forth, the destruction, if you will, of the meteoroid by the heat at its forward surface. And for a few seconds, it becomes quite bright. If anything is left at the end of that bright flaring trajectory, that doesn't mean that, or when the meteor dims and goes out, that doesn't necessarily mean that there's nothing left there. There could be a meteorite which is now falling at essentially terminal velocity. It's slowed almost to zero, and it continues to fall. It's not glowing anymore, but for several minutes, it will fall from stratospheric heights, typically where airliners fly, to hit the ground. And so that's what happened for the Grimsby meteorite, for example. After the fireball itself ended, the meteorites continued to fall for several minutes. And you actually have to take into account winds and so forth that are blowing in order to find where the meteorites land. They don't just fall straight down. Also, a meteorite, when it hits the ground, will not hit at tremendously high speed, typically, not for these small sizes. And it will also tend to be cold, because it spent a lot of time in the stratosphere, relative to the very brief heating that it received on the way down. Okay, but could meteoroids arrive from other stars? Well, there are a number of sources of these particles. The most obvious, perhaps, is other solar systems. So it's estimated that about 1/3 of all meteoroids which are produced in our own solar system eventually get ejected at all sizes. So that's a lot of material. So that's definitely a possibility there. Asymptotic giant branch stars, or AGB stars, are thought to be the dominant contributor to what astronomers call dust, small solid particles, that exist in interstellar space. And they're stars near the end of their life. They puff up and they blow off the outer layers of their surface. That material is very rich in carbon and oxygen, which crystallizes into small grains, which are observed by astronomers through telescopes. So these could obviously enter our solar system as meteoroids as well, though they're mostly small stuff. Young stellar objects are planetary systems that are, or star systems, planetary systems which are currently forming. So the scenario for planet formation is complicated, but it involves a period where the solid materials in the cloud coagulate to form larger and larger particles, which eventually become planets. This process is very messy, and a lot of the material actually gets ejected out into space during this time. And so YSOs are likely sources for interstellar particles. And debris disks. And so a debris disk is the only one I'm going to show a picture of, but a debris disk is something intermediary, if you will. Planetary system partly formed or stopped mid-formation. So this is a Hubble Space Telescope image. The star is sort of in this black area, and it's been masked out because it's too bright. So we can see the very faint details which are out here. So this is a disk of dust which surrounds this star Beta Pictoris, and it's much larger than our own solar system. It's, exceeds the size of Pluto's orbit. This is a sort of the true color image, if you will. This is a false color image designed to enhance some of the details. And so Beta Pic has actually been fingered as a possible source for interstellar meteoroids, because it's quite controversial. So, could we get a meteorite from another solar system? Well, the magic number is that if you want to get a meteorite on the ground, on the Earth at least, you need something which hits the top of the atmosphere that's about a meter in size, maybe a few meters, depends on the composition, but that's what you're looking at. But in our own solar system, small meteoroids are much more abundant than large ones. And sort of, for this group, this is much too vague, but if you decrease the size by a factor of 10, you can decrease the number by a factor of 1,000 or so. So there's a power law which sort of follows that trend, though there's a lot of actually some play in there. It could be quite different to a first approximation. And if this holds for interstellar meteoroids, then it's going to be very, very hard to find actual interstellar meteorites. But we're going to sort of do the math if we can. So maybe the first question, particularly here, we're thinking of the possibility of maybe transporting life between the stars, for example. That's sort of the ultimate question we might want to ask. The rocks themselves, of course, are interesting. But inevitably that question arises. And so first we maybe should mention the possibility that meteorites can travel between the planets. In fact, it's quite commonplace. First of all, computer simulations show that you certainly can eject objects, rocks, if you will, intact, at sizes larger than about 10 centimeters from planetary surfaces without shocking them too much. And what too much means is, of course, it depends on the organism and a lot of other things, but it's probably not implausible that you could do this. Now, the number 10 centimeters is here because that's another magic number as far as I can garner from the literature. If you want to put, say, bugs or microorganisms from a planet to another, the number that often gets tossed around is that you need the rock to be at least 10 centimeters across for it to survive in it. It sounds like that's a pretty controversial question, but that's sort of a number which seems to get discussed, given my very cursory perusal of the literature anyway. Certainly it's accepted that meteorites from the moon and from Mars are in our collections right now. Sort of a dozen of each, and I would say that's not too controversial a result, and so that means that rocks at least a meter across have been launched into space from these two bodies. It's questionable whether or not we have meteorites from other planetary bodies in our collections right now. Mercury has been fingered in the case of one meteorite, but I would say there's no real consensus there. In fact, it's estimated that about half a ton of Martian material, or about 15 individual meteors, hit the Earth every year. Now, not all of those reach the ground. Of course, many of them fall over oceans and so forth, but even now, when there's not a lot of interplanetary transfer going on, it's still still going on fairly actively. But from other star systems, that's got to be a little bit harder for sure. So this analysis I had nothing to do with. It's mostly from Malash 2003, who wrote a nice paper on this. But the interstellar transfer of meteorites is difficult. But if you work on the assumption that about 1/3, well, not assumption, but some computer simulation results have shown that about 1/3 of material of meteoroids in our solar system get ejected, then you can work out that about 100 rocks from the terrestrial planets, so not necessarily from Earth, but from Mercury, Venus, Mars, the Moon, and so forth, larger than 10 centimeters in size, are ejected from the solar system every year. So once they leave the solar system proper, they travel out into interstellar space, essentially on straight line trajectories, at speeds which are, well, around 10 kilometers per second. So a parsec, which is the distance between us and the nearest star, is about 200,000 astronomical units. Do the math. It takes about 100,000 years, a few 100,000 years to get from our solar system to another planetary system. Could microorganisms live that long? That's a question I can't answer. But then you need to ask whether or not it could actually hit another terrestrial planet in that solar system. It turns out that the odds are not particularly good. In a billion years, you get a number of 10 to the minus 4. Now you might say, oh, that's actually pretty good, because you've got 100 rocks per year times a billion years. That's a lot of rocks. But unfortunately, this is the number, this is the odd that one of those 100 billion rocks that you launch will hit a terrestrial planet. It's small. And the reason for that is just that space is incredibly big. You have put 100 billion rocks out there into a volume which is some ridiculously large volume. And so there actually turns out to be only about one of these rocks per volume, which is sort of equivalent to our own planetary system. So if you draw a box around Neptune and you make that volume 1 unit volume, you end up with only one rock in that volume once you get out to a parsec. And so even though you put a lot of rocks out there, space is huge. If you just ask the question, well, what if you just want to get captured by another star system? A little bit easier to do. You still only get 1 per billion years. So that's not a lot. It does mean, however, that if other star systems work kind of the way ours does, there should be one rock from every star system near us in the galaxy, which is captured in our solar system every billion years. And they may still be out there, but we're talking about incredibly tiny numbers. Optimists say, well, these numbers would have been much higher during solar system formation, for example, and they would have been by orders of magnitude, thousands of times, without too much difficulty. But it's the idea of whether or not life could survive these kinds of journeys remains sort of an obstacle always. So it's still quite a controversial field. Maybe just possible, but not very easy to do for sure. So I'm going to talk a little bit more about interstellar meteoroids, which are smaller, and so they're more abundant. A big problem, though, is that how do you identify these as coming from another star system? They don't come with that sort of a label attached, made in Gamma Cygni 4 or something like that. So if you get a big enough piece, you might be able to do an isotopic analysis. If the isotopic ratios are different from our solar system, you might be able to do this. If you recover it in space, this is certainly more of a possibility than if you try to do it as it burns up in the atmosphere. So as you know, there's a big meteor physics group here. Meteors are observed as they burn up in the atmosphere. Spectroscopy might be used to do this, but doing spectroscopy on isotopes in the atmosphere is difficult because you might be interested, for example, in oxygen isotopes. Well, the atmosphere is full of oxygen, so how do you extract the signature, the oxygen signature you're seeing from the atmosphere and so forth? So what is typically looked for, people have looked for interstellar meteoroids before, and they've used high velocity as the signature. The idea here is that if you see a meteor, so the escape speed at the Earth's orbit is 42 kilometers per second. So any particle which crosses the Earth's orbit traveling more than 42 kilometers per second is not bound to our solar system. It must have come from outside the solar system. It's going to leave and go back out into interstellar space, but the argument is that it does not come from within our solar system. And so if you see meteors that have these high velocities, in the past, papers have claimed that these are interstellar based solely on these high velocities. And the argument behind it is not terrible, it's just not particularly watertight. But if meteoroids are coming to us from other stars in our vicinity, we'd expect them to enter the solar system with this extra velocity, this extra energy, which would be typical due to the motion of stars in our galaxy. So our galaxy is full of stars, they're all moving around the common center, but they also have random velocities, which are about 20 kilometers per second. And so you'd expect meteoroids to arrive at our solar system traveling 20 kilometers per second faster than they would otherwise be if they came from our solar system. So because energy and not velocity is conserved, it means that they arrive at the Earth with a velocity of maybe 66 or 67 kilometers per second, which is above the 42 kilometer per second escape speed at the Earth's orbit. And from that, we would like to say that they are interstellar. And so this excess velocity is what has been traditionally looked for. So, well, have they been seen? And the answer is yes, but. The key is maybe down here, and that is that excess velocities of order a few kilometers per second have been measured, but the measurement techniques used have errors around 10%. So you start with 42 kilometers per second, the excess velocity is 4 kilometers per second, it's pretty obvious that what you're measuring is sort of order the error. And so though these have been reported in the literature, there's been quite a great deal of controversy about whether or not they're real or not. And as people have gone through and tried to do better and better jobs of reducing the error, the number of interstellar meteors reported has gone down dramatically. So there's been some question as to whether or not we can even measure these yet. And this is recognized even by the folks who are reporting these. So this is from probably the most famous paper to report interstellar meteors by Jack Bagley in 2000. And he recognizes that this has been a problem and continues to be a problem. But certainly I would agree with him that as we get better and better at this, we could maybe do something which is a little more realistic or believable. So there have been what I put reliable detectings here. Maybe I should have just put non-controversial detection because that's a bit of editorializing here. But very small interstellar meteoroids, smaller than about 10 microns, have been seen by spacecraft in space. Observations of their direction and velocity over time have convinced most people, myself included, that these are coming from interstellar space. They're very, very small. They're tiny particles, so small that they can't even really be measured on Earth. They're that small. These particles are small and are actually entrained by the local gas. So interstellar space is not empty. There's actually some gas out there, and it flows. The Earth, the solar system is traveling towards what's called the solar apex, and the gas sort of streams around us. And these meteoroids are coming from that direction. They're actually being dragged along by the gas. They're too small to detect as meteors on Earth. They're very, very faint, of course, which makes them hard to detect. But at the smallest sizes, they actually don't even burn up in the atmosphere. They're so small that they're so efficient at re-radiating the heat they generate as they hit the atmosphere that they just slow down, radiate away their heat, and drift down. They don't produce any optical light at all. So you might be able to collect them. In fact, they have been collected by aircraft, not interstellar ones, but it's very small particles. But it's hard to measure their velocities at that point. Spacecraft dust detectors are probably the best detectors for doing this, but they're typically about the size of a dinner plate. And so they just don't get hit by very many larger particles. The other interstellar meteoroids that have been reported by radar and optical systems based on the Earth and watching sort of for them to burn up in the atmosphere remain controversial because of this velocity error consideration. Better and better studies have been done for sure, including some by people here at Western. But as you increase the precision, the number of interstellar meteoroids decreases, which makes people nervous because about the earlier reports. So radar and optical systems can measure these larger particles because they monitor a much larger portion of the sky, so you actually get an appreciable number of these small guys. At this size, it starts to get kind of exciting because they're actually massive enough to maintain a straight line motion through the galaxy. They're not dragged along by the gas, and so you can actually hope to start to do meteor astronomy, where you can actually, instead of looking for photons coming from a particular source, you can look for meteors coming from a particular source and actually sort of image them on the sky, which would be quite exciting. If you could say this meteor came from Alpha Centauri or something like that. Again, all the usual caveats about how to identify them apply. So how do we make progress in this? Well, you need to measure the velocities more carefully. You need to make sure your measurement techniques are very well understood, and some folks here at Western are working on that. And we need to also understand whether processes wholly internal to the solar system can produce excess velocities comparable to those observed. So this is the only real bit that has anything to do with the work that I'm doing. But a meteoroid in our solar system passing close to a planet can actually acquire a certain amount of velocity. I already mentioned that meteoroids are ejected from our solar system. That means they must leave on velocities which are above the escape velocity. So our solar system actually produces these. You may know this as the slingshot effect, which has been used to great advantage by many spacecraft. Meteoroids, of course, don't use it deliberately, but there are so many of them in the solar system that some of them just happen to end up on the right trajectory. And so I've done some computer simulations where we bombard the planets with meteoroids from all different directions. They don't really come from all different directions, but to get an idea of whether or not the planets could produce these hyperbolic meteoroids from our own solar system. So some of you will have seen this, but this is Jupiter here, and these are just the meteoroids which will arrive at the Earth on hyperbolic trajectories. So all the other ones I've just left out because it just gets too messy. And you can see that Jupiter is bombarded by some meteoroids which are wholly internal to our solar system, but which arrive at the Earth with high velocity. And the highest velocity ones are labeled here in blue. Blue indicates a meteoroid which arrives at the Earth with a speed which is greater than 1 kilometer per second above the escape velocity. Most of the other yellow ones are sort of just above the escape velocity. They're really close to the limit. You can do this for all of the planets. So this is for Saturn. Saturn doesn't do quite as good a job. It's not as massive. It moves more slowly, but you can see that it can also produce some high velocity meteors. And the last one I'm going to show here is Venus. So again, we're only showing the ones which cross the Earth's orbit. Venus can't really produce high velocity meteors, but it can produce some just above the hyperbolic limit. And so if you plot these up, well here I'm just plotting the ones for Jupiter, but you can see that for Jupiter, again remember 42 kilometers per second is our escape velocity, plus 4 or 5 kilometers per second is what we expect for interstellars. You can see that Jupiter can actually produce, in small numbers for sure, meteoroids which would look a lot like hyperbolic meteoroids. So you can't just measure the velocity, but if you're clever and you measure the velocity and you know the time and so forth, you can actually backtrack these meteoroids. You just use a computer simulation to see if they came from a planet or if they came from interstellar space. You don't just take the velocity as a raw number. So just being a little more careful and taking a little bit more data is valuable here. And so these are just to show you what the other planets can do. You can see that none of these planets, except maybe Saturn and Venus, can even get up to 1 kilometer per second. The other ones just don't do very much. So Jupiter is really the big player here. So this is just a summary of the theoretical results, but I really only want to talk about this point here. High precision velocity measurements should allow the true nature of these things to be assessed. And so this, of course, is a segue into some of the meteor work which is being done here. Some of you will have already seen this, but there's a meteor observatory, which is run by some of the people in this room here, that is specifically set up to do very high precision velocity measurements, among other things, of meteors, not specifically to look for interstellar meteors, but interstellar meteors should be picked up in this process if they arrive at the Earth at all. And so the idea, again, you've seen these slides before, you've got two different stations which stare at a common volume of space. One of it sees, maybe this kind of video on the frames, the other one sees video like this. You combine all of the information with the geometry, and you can get all the information you need about the path of the meteor through the atmosphere, which tells you about where it came from once you back that up. So the observatories are here at Elgin Field in Tavistock. This is what they look like. Well, no, this is actually the Keck Observatory on top of Mauna Kea. I wish I could tell you that it looked like this. The actual observatory looks a little more modest. Sort of this garden shed and this little trellis over here. The roof will move off using the garage door opener and then close when the meteor observatory is done. What's really brilliant about this is that it's all computer operated. So the computer decides if the weather's good enough, if it's dark enough. It opens the roof, it starts taking data. If the weather turns bad, it will close the roof. It will analyze the data and will send you an email in the morning telling you how many meteors it found. So real kudos are deserved by the folks who have put all of this together, some of whom are in this room. So it's quite a clever little system. This is the other station here. It's located on a farm. You can see the farm over here. And just a picture of some of the guts inside here. So there's a camera which looks at the entire sky, well not the entire sky, but which looks at a large portion of the sky. And when a meteor is detected, the computer is constantly monitoring the video from that camera. A higher resolution camera kicks in here. And the clever bit about this, of course, is that, well, if you want to study meteors really well, it would be nice to zoom in on them with a telescope, the way you do any other astronomical object. But because meteors move so quickly across the sky, it's impractical to get a giant telescope and try to pivot it across the sky at that speed. It's just not mechanically feasible. So what you do instead is you get a couple of pivoting mirrors which will actually deflect the light from the meteor into a telescope where the telescope itself stays stationary. So the telescope is actually here. But you've got some computer-controlled mirrors which will deflect the light into the telescope, which is sort of equivalent to having the telescope look where the meteor is. Very, very clever. So this is just a picture from the wide field which shows, this is just in a loop, but it just shows the camera automatically detecting a meteor here. Some of the other ones are a little bit brighter, hopefully you'll be able to see them. But then when you go to the mirror system, you can see, this has been slowed down a little bit, but you can see a real zoomed in view of that meteor. I'm not sure if this is exactly the same meteor, but it's been slowed down and stretched a little bit. You can see a little bit of bouncing around there as the meteors try to get on the proper tracking. You do lose a little bit of information at the beginning, though the algorithm is always improving for doing that. But you can see that you can get a very nice, clear, close-up view of the meteor over time. This one is one of the more spectacular ones that have been picked up. Again, these particles are very small. They might be almost invisible to the naked eye. We're talking particles sort of in the millimeter size range, below a millimeter. And you can see here it breaks up. Again, this is slowed down, but you can see it break up into all its individual little particles. Very, very interesting look at the inside of an interplanetary grain at the very least. And here, just to show the distances involved between the sizes of the particles are hundreds of meters. So you've got a very tiny grain which is breaking up and spreading by tremendous distances. This is very exciting, even not as an interstellar phenomenon, but even for interplanetary meteors, this is not understood. And there are papers in the literature that will tell you that this can't happen, that particles can't spread by this much, at least not by standard aerodynamic forces and so forth. And there are people here studying that as well. We'll have to get lots more people from the meteor group to talk to explain all of this stuff. And so here is just a plot of the breakup of the different positions and so forth. So again, this is not my stuff. This is stuff by some of the other folks in the meteor group that I'm going to acknowledge in mass at the end. So the results so far, you might ask us, have you seen any interstellar meteors already? Tell us the answer. And the answer is we don't know yet. We've reduced about 1,800 meteors that were taken during the summer of 2010. And there are some that are above our hyperbolic limit by what we think are 3 sigma or more. But again, 3 sigma is sort of what we think the errors are. It's a complicated system. We're really only starting to characterize it, and so we're hesitant to say, yes, we found them. In particular, if they really are hyperbolic, they seem to be only 1 or 2 kilometers per second above the hyperbolic limit, not the 4 or 5 that would put them in the clearly interstellar, well, even not then clearly interstellar, because the planets can do that. But they're sort of a little bit in that gray zone where we're not quite sure what to make of them. They may be hyperbolic, they maybe have been generated within our own solar system. Maybe they're just slow interstellar meteors, or maybe we don't quite understand the errors of the system yet. But we've been banging on them for a little while now, and they haven't really shaken loose completely yet. So we still have some hope for that. And so I'll just summarize here to say that interstellar meteors at very small sizes have almost certainly been detected reliably. Larger ones are getting into sizes where we could see where they could come from, or even where they could carry stuff with them, like life, almost certainly exist at some level, but they have not been detected with any kind of reliability here in Europe. We're hoping that the Canadian Automated Meteor Observatory is going to provide some more insight to exactly what's going on here, but we don't have any results yet. And so a long list of acknowledgments of people here in the meteor group that are responsible for most of that exciting work. So thank you very much.
Thanks, Paul. We have lots of time for questions.
So the 3 that get found were, did you prove that none of them were influenced by Jupiter?
Actually, we're just running that now, and it looks like they did not pass particularly close to Jupiter or any of the planets. So it's still the early stages, and I need to make sure that everything's working right, but they seem to come to us from interstellar states. That said, I mean, it is still a preliminary result. Yep.
So, out of curiosity, the initial projections for the number of meteors that are ejected from our solar system from terrestrial bodies.
Yes.
Does that is that calculation just due to velocities of the ejected particle at the moment of impact, or does that include things like Jupiter spitting them out of the solar system as well?
Yeah. So the ejection of these particles into space is not actually due to asteroids crashing into Venus or Mars or Moon or the Earth this year and ejecting those particles into space. So I don't want you to give the impression that
No.
the planets are
Historically
being
speaking.
monitored. Or even historically speaking, what happens is that these particles might have been, so the time it takes to go from being released from a planet to being ejected into interstellar space, which is often through the slingshot effect interaction with Jupiter, might be 50 or 100 million years. So these are particles that were actually released from the planet or ejected from the planet tens of millions of years ago, have been orbiting within our solar system. Eventually, by chance, happen to have a close encounter with Jupiter, which slingshots them out into space. And so we expect that about 100 of these types of particles are leaving the solar system per year, but they're not leaving the planets on a yearly basis. So that actually plays into the question of whether or not life could survive this passage, because they might actually spend longer in our solar system before they get ejected, and it will take them to travel to nearby stellar systems. There seems to be some debate as to whether or not any kind of bugs could live for 1 million years on a little rock in space. But that's not something I can comment on knowledgeably.
At the other end of the distance scale, how many of these things falling into the atmosphere are our own chickens coming home to roost?
That's a good question. And people have asked the question, how many rocks ejected from the Earth eventually just fall back to the Earth? And the answer is, we don't know. No meteorites have ever been identified as being from the Earth. Of course, if you found a rock on the Earth, how would you know? It could be a meteorite, unless you actually saw it fall through, and you find it and it was fresh enough that you could. So the answer is, I think that no meteorites from the Earth have ever been discovered. But it would be very hard to find them and convince people that it wasn't an Earth rock that we did. So. Yep.
So you mentioned about the dust detectors on some of the outer solar system orbiters, and that being a very good way to get an interstellar origin.
Yes.
They have problems with the size, with some of the different size. How big a detector would you need to make it practical?
Well, again, because every factor of 10 decrease in size means for 1,000 times fewer particles. So if you want to detect particles which are 10 times bigger, you need to make your detector 1,000 times bigger in area. So you can see that going from 1 dinner plate to 1,000 dinner plates is already a big leap, and that only takes you sort of maybe to 100 microns in size. So that rule of thumb is probably what you need to go with. Every factor of 10 in size you want to increase to detect reliably, you need to increase your detector area by about a factor of 1,000.
So a couple of meters might help.
It wouldn't hurt, but if you want to detect really big particles, you start to get impractically large detectors. And most of these detectors are really designed to detect solar system dust, where the smaller size is fine because you get so many particles. It's just a small fraction of them that are interstellar. So it's hard to sell it to the granting agency that you use this giant dust detector to detect 3 interstellar meteors.
Fair enough. How do those compare to, say, just clipping big chunks of aerogel?
Well, that would be, the Stardust mission has spent part of its time trying to collect interstellar meteors. So it basically has this aerogel collector, and you wait for meteors to impact in it. Aerogel, I think, would be a great way to do it. It does have some difficulties. You lose all the information about exactly where it came from. You can't back it up. In other words, it hit the gel, but you don't know really at what speed it did or when and so forth. So there's always going to be a little bit of a question there. But you do potentially get compositional information that you can't get by other means. Now, I understand that impacts in aerogel do volatilize some of the components, and so you've got all kinds of, it doesn't matter what you do, there's always some gotchas in it. But I think doing a combination of meteor observations and some kind of aerogel collector would be a good idea if you're interested in these things.
So I'm wondering what kind of things you look for in big micrometeorite collections, because there are very big micrometeorite collections that might have some defining characteristics for extra solar system meteorites.
Well, if you tell me the isotopic ratios of some of the nearby stars, then I can tell you what the answer is. But I'm not sure that that's tremendously well known. If you could demonstrate that there was a class of micrometeorites that had an isotopic signature that was outside the acceptable bounds for production within our own solar system, that would probably be acceptable. I don't know enough about isotopic ratios to tell you. I do know that some meteorites have what are called pre-solar grains in them, which are presumably grains which have come from other star systems that actually survive the planet formation process relatively intact. I don't know, those might give us a hint as to what kind of isotopic ratios to expect, but I know very little about those.
It's another question. So there are freaky grains and organic conrays that are pre-solar. Do they count?
Sure, they count. Well, I mean, it all depends on whether you want to, they arrived at our solar system before our solar system almost existed. But, and there's no shortage of these solid materials in interstellar space. So certainly we have received a tremendous amount of interstellar material over the lifetime of our solar system. But whether it's happening now at what level and whether this could, the question always gets asked, could life travel on these kinds of things? And I haven't been able to find any definitive answer. I'm not an expert, but I tried to read a couple of papers on this before we talk. Maybe somebody here, we have people who know about extremophiles in this room, maybe they could comment on whether or not a bacterium or a tardigrade, which seems to be the favorite little bug to send through space, might be able to survive for millions of years. I'm not sure.
Well, we could start an experiment today and collect it in a million years.
That's right. Definitely a PhD project.
Go into stasis and wait it out.
Stone 6 or something.
Yeah, there's been quite a few experiments setting up, strapping up the space station and looking at that. Stone 6 was to rocket, was it Soyuz?
Yeah, slowly rock with bugs in it on the front of the Soyuz capsule.
Yeah, some of it was shot nice and important. But that's just days and weeks.
Yeah. I think there have been, there are microorganisms of various kinds which can survive vacuum for some short periods of time and hard radiation for some, again, these experiments have run for days or weeks. But a million years is something really different.
They're pushing a million years from permafrost around. And again, extrapolate that for 100 years.
The longest one I know of is about 5 years for surveyor cameras by the astronauts. And that wasn't particularly hardy stuff that came back alive from inside.
There's a lot of doubt about whether that's actually true, I should point that out because there's considerable evidence that was due to post-collection contamination. So, although the story still keeps getting circulated, that is very suspect.
Well, that's good to know. We'll get a good answer once we go to Mars.
That's right.
Get to open up some of our electrons.
Yeah.
All right, thanks, Paul.